7. External forced convection. Let's talk about external forced convection. When we say forced convection, we mean situations where the fluid motion, like air or water, is driven by external means, such as a fan, pump, or wind. This is different from natural convection, where the flow happens because of temperature differences alone. Think about a car driving on a highway. The car's surface heats up under the sun, but the air rushing past it quickly removes the heat. That's forced convection in action. The wind cools the car faster than if it just sat there in still air. In this chapter, we'll see how to calculate heat transfer in these situations. We'll learn simple methods to estimate how much heat is carried away by the moving fluid using things like the Nusselt number, Reynolds number, and Prandtl number. Remember, forced convection is all around you, from the cooling of your laptop by a fan to the design of wind turbines. By the end of this, you'll know how to quantify it and design more efficient systems.
1. Learning outcome. Let's go over what you'll take away from this chapter. In heat transfer, it's easy to get lost in equations, so these learning outcomes will keep you focused. First, you'll clearly know the difference between internal and external flow. This is key because flow inside a pipe behaves completely differently than flow over a flat plate or a car's surface. Next, we'll tackle drag forces. There are two types: friction drag, which sticks to surfaces, and pressure drag, which comes from flow separation. Understanding these helps you figure out how much energy is lost in moving fluids. Then, you'll get hands-on with flow over flat plates, especially learning how laminar flow, the smooth kind, transforms into turbulent flow, the chaotic kind, and what that means for heat transfer. We'll also cover how to calculate drag and heat transfer for common shapes like cylinders and spheres. These are everywhere in engineering, from pipelines to sports balls. Finally, we'll look at tube banks, both inline and staggered. You'll learn how these arrangements change pressure drop and heat transfer, which is crucial for designing heat exchangers. If you can check off these 5 points, you've mastered external forced convection.
2. Introduction to external forced convection. Let's break down what external forced convection really means. This happens whenever a fluid, like air or water, flows over a solid surface. A simple example is wind moving over a car. The motion of the fluid isn't natural, it's driven by some external force, like a fan, a pump, or, in this case, the car moving forward. One of the most important things to understand here is the concept of a boundary layer. As the fluid touches the surface, it slows down and forms a thin layer called the boundary layer, which keeps growing the farther it flows. This layer controls both the heat transfer and the friction on the surface. Finally, you'll learn that there are two kinds of drag at play: friction drag, which comes from the stickiness of the fluid against the surface, and pressure drag, which comes from the shape of the object and flow separation. Together, they help explain how much force the fluid applies and how effectively it carries heat away. In short, external forced convection is what happens when moving fluids interact with solid surfaces, creating heat transfer and drag forces you can actually calculate.
3. Drag and heat transfer in external flow. Let's talk about drag and heat transfer in external flow. Whenever an object moves through a fluid, or a fluid moves past an object, it experiences drag or resistance. That's called drag force, and it's the reason your car uses more fuel at high speeds. To quantify this resistance, we use the drag coefficient, CD. It's a normalized number that shows how much drag an object experiences relative to its size and speed. The equation includes the drag force, fluid density, velocity squared, and a reference area. There are two main sources of drag. Friction drag happens because of the fluid sticking to the surface, what we call wall shear stress. This is crucial for sleek, streamlined designs like airplanes. Then there's pressure drag, caused by pressure differences from flow separation. This dominates in blunt objects like trucks or buildings. The total drag is simply the sum of both, friction drag plus pressure drag. Understanding this breakdown helps engineers design faster cars, more efficient turbines, and better cooling systems by knowing where the resistance really comes from.
4. Flow over flat plates. Let's simplify the idea of flow over flat plates. The first thing you need to know is when the flow changes from laminar, smooth and ordered, to turbulent, chaotic, and mixed. This happens at a Reynolds number of about 500,000. It's a handy shortcut. Below this number, flow is calm. Above it, things get wild. Next, we talk about friction. Laminar flow has less friction, and we can predict it with a simple equation. But when the flow turns turbulent, friction increases, and the formula changes to account for the messier flow behavior. Finally, heat transfer. That's where the Nusselt number comes in. In laminar flow, the equation depends on the square root of Reynolds number and Prandtl number. For turbulent flow, it's a bit more complex, with the Reynolds number raised to the power of 0.8. These formulas aren't just academic, they help engineers predict how much heat a surface will lose or gain when fluid flows over it. That's crucial for designing things like aircraft wings, car bodies, or cooling plates.
5. Flow over cylinders and spheres. Let's look at flow over cylinders and spheres, two classic cases in external convection. With blunt bodies like these, the flow can't stick to the surface all the way around. It separates, leaving behind a wake, a messy, swirling region of low pressure that increases drag. The drag coefficient behaves very differently based on the Reynolds number. At low Reynolds numbers, we have Stokes flow, where drag is predictable and decreases as flow increases. In moderate ranges, the wake gets bigger and drag goes up. At very high Reynolds numbers, something dramatic happens: drag crisis. The boundary layer transitions, and drag can suddenly drop. For heat transfer, we use the Nusselt number. Cylinders have a more complicated relationship because of the wake and transition effects. Spheres are a bit simpler, with formulas that consider both the smooth and chaotic parts of the flow. This section teaches you how to predict heat transfer and drag for real-world shapes like pipes, wires, and balls, things you see in engineering, sports, and nature.
6. Heat transfer and drag reduction techniques. Let's finish with some practical ways to reduce drag and improve heat transfer. The simplest trick is streamlining. When you smooth out the shape of an object, like an airplane wing, you shrink the wake and cut down pressure drag. That's why race cars and planes look sleek. But here's a twist. Surface roughness doesn't always make things worse. Depending on the Reynolds number, roughness can either increase or decrease drag. In some cases, it actually helps by tripping the flow into a more stable turbulent layer earlier. A classic example is the golf ball. Those dimples are there on purpose, not for style, but to delay flow separation. By doing that, the wake is smaller and the ball flies farther with less drag. In short, engineers play with shape and surface texture to make things move smoother and transfer heat better. Small tweaks can make a big difference.
7. Flow across tube banks, one of the most practical topics in heat transfer. Tube banks are everywhere in industry, inside heat exchangers like condensers and evaporators. The way the tubes are arranged makes a huge difference. In-line arrangements, where tubes line up, cause more pressure drop, but are easier to manufacture. Staggered arrangements offset the rows, which promotes better mixing and improves heat transfer. For calculations, we use the Reynolds number based on the maximum velocity between tubes. It captures how fast the fluid squeezes through tight spaces. The Nusselt number predicts heat transfer rates and changes with flow patterns. It's affected by flow speed, fluid properties, and even how hot or cold the surface is. You'll often see equations with coefficients and exponents that vary based on the design. Finally, pressure drop is key. Higher pressure drop means more pumping power is needed. Engineers balance this carefully. Enough turbulence to transfer heat, but not so much that energy is wasted pushing fluid through the system. This is where heat transfer theory meets real engineering design, getting the most cooling or heating with the least energy cost.
8. Engineering applications. Let's close with how these concepts apply in the real world. In automotive design, reducing drag isn't just for speed, it's for saving fuel. The less resistance a car faces, the less energy it needs to move, making it more fuel efficient. In aerospace, the focus shifts slightly. It's not just about cutting drag, but improving the lift-to-drag ratio. That means getting the most lift for the least amount of drag, which is essential for efficient flight. In heat exchangers, it's all about optimizing tube banks. Engineers carefully design them to increase heat transfer efficiency while controlling pressure drop. Better tube arrangements lead to more compact, cost-effective systems. These examples show how mastering external forced convection leads to smarter designs, whether it's faster cars, more efficient planes, or better industrial equipment.
9. Summary. Let's close this chapter with a quick recap of the key points. Drag and heat transfer always circle back to one thing, the Reynolds number. It tells you how the flow behaves, and that affects everything from friction to heat transfer rates. Flat plate solutions are simple but powerful. You'll see them used all over engineering, especially when designing smooth surfaces like car panels or solar collectors. When you move to cylinders and spheres, things get more complicated. Flow separation creates extra drag, and predicting it requires a deeper understanding of wake behavior. And for tube banks, you can't just guess, you need specialized equations. These correlations help balance heat transfer efficiency with pressure drop, which is crucial in industries like power plants or refrigeration systems. Master these 4 points, and you've got a solid grip on external forced convection.